for the opportunity. My name is Abdel Nasser Tawfiq. I'm located in Cairo, and I'm going to speak about a proposal which I'm going to present to the collaboration. It deals with an idea on how to measure the equation of the state in the CBM experiment. That is very simple. In the experimental side, we have some limitations in what we can measure. On the experimental sides, we have also other limitations on what we can measure, but both of them are not agree on measuring the equation of state, with which I mean the thermodynamic quantities. And the agenda of my talk is I start the first part with kind of assessment or reviews what we have, the situation we are dealing with right now, and the second part is a kind of recipe, kind of proposal methodology on how we can measure the equation of the state experimentally. What we do, what we have in the nuclear experiment is that we start with projectiles, energetic projectiles. We start with energetic hadrons or leptons, depends on your collider. Then we make the collision, and the collision evolutes in time. Then we have at some time we can put, or we can switch on our detectors to measure the output. The outputs are nothing but also again energetic hadrons and leptons. What's going on in between, we couldn't access with our experimental tools because of many limitations here. It is very similar case to if you are going to take a photo of liquid water or cup of water, you cannot tell whether the water is coming from ice or whether the water is coming from vapor. To do this, you should have some kind of video picture or video film to tell this, and this we don't have right now, I guess, from the experimental point of view. Not only this one, this point is our limitation, experimental limitation, but also what we measure actually is limited. What we can measure is our characteristics of well-identified direct or produced particles, or also same for not well-identified produced particles and produced indirect particles, but also we are assuming extensive statistics. We are applying Boltzmann statistics, which works very well for ideal gas, for equilibrium system, and this is not the case in our experiment. Our experiment, it deals with strongly interacting matter, in which we have dynamics, we have collisions, and we have evolution. With this extensive statistics, we are just hiding, we are just ignoring the dynamics in the system. What we cannot measure are the temporal evolution of the collision. We cannot detect the partonic degrees of freedom, and of course, we are not able to detect or to measure any of the thermodynamic quantities, and this is what I'm going to present. What are the equations of the state? What I mean with this, they are a measure of the response of our system to some intrinsic extreme condition like temperature, like density, and so on. The response is the equation of the state. The thermodynamic state is characterized. This should be noted, characterized under some given physical condition. For example, constant density, constant entropy, and so on. The equation of thermodynamic equation of the states relates some thermodynamic variables, for example, pressure, energy density, and so on. And people usually use the Helmholtz free energy to measure the state. Why are important this equation of the state? Because we need them to understand the evolution of our universe. The Friedman solution strongly depends on the equation of state we are introducing. We can get a flat universe, or even open or closed curved one. Even recently, when we are confronted with the neutron star mergers and even black hole mergers, we need to introduce various equations of state just to relate the mass with radii and so on. Therefore, the equation is important. Yeah. What are the situation of our knowledge about the equation of state? For the early universe, I'm just showing here non-perturbative QCD compared with perturbative QCD. The non-perturbative one are these blue as the upper blue symbols, which are higher than the non-perturbative. That's QCD. But if we manage to make some scaling, we can have this middle panel in which we could scale, or we could match the non-perturbative lattice QCD with the perturbative one. The measure, or the indicators that our matching, our scaling is correct, is measured by this line here, the thin line, which is the effective degrees of freedom, and you can see there is a continuity in the effective degrees of freedom. Therefore, we think that the panel on the right-hand panel gives the equation of state, which relates the pressure to the energy density to very high temperature. This is what we have now from the lattice QCD, or from the QCD, either perturbative or non-perturbative. Doing this, we can propose a paratropic equation of state, with which I mean the relation between any thermodynamic quantities to the energy density. And this is important if you are interested in cosmology, because you can replace the energy density by the Hubble parameter and so on. Then you can, and afterwards you can continue your calculation. And you can see here from this picture that the pressure related to the energy density could be related to very high energy densities and pressure. Even we think we could cover the electroweak era in the early universe. This is what we have from the lattice QCD, so from the computational. Again, from the computational side, the perturbative lattice QCD is limited to a global assumption of an overall thermal equilibrium in both hadronic and partonic phases. And this is a kind of approximation which we have to live with, we have to survive with, because we don't have other alternative. We don't have the technology to deal with asymmetric lattice QCD. As a complementary to the perturbative QCD, we have the non-perturbative one, which allows us to go to higher temperature. But both of them, the reliability is limited to vanishing densities. I mean, if we go to higher density, finite density, the reliability of the lattice QCD still needs to be careful to give any, or to draw any conclusion. We can do this when we use the so-called QCD-like effective model. For example, the Polyakov linear sigma model, which could be classified as the complementary to the lattice QCD at large density. It allows us to go to higher densities, even to cover the region where the CPM is going to work. And the other important feature of this effective model is that the dynamics here is included, especially the chiral dynamics, whereas in the lattice QCD, the perturbative one, there is no dynamics at all. I'm just showing you some results from the perturbative QCD. Here's the equation of the state. Here's the pressure and energy density, and even the entropy on the left-hand side. And you can see the increase is very slow, and we used to call this rapid crossover. It is not a real phase transition. And on the right-hand side, you can see the interaction rate, the quantity, which is epsilon minus 3b, normalized to the to t to the power 4, and you can see even at high temperature, twice or even 3 times the critical temperature, we still have interaction in our system. It means that the system in the lattice QCD is below the Boltzmann limit. Nevertheless, people used with the thermal model and so on, used Boltzmann statistic to do this. Again, here is the non-perturbative QCD, which allows us to include many quarks, up to 6 quarks, the entire standard model. And we could compare this with non-perturbative QCD for us to have an idea or an access to the equation of state. From the other side, from the QCD-like model, we can do the same. You can see here the pressure as a function of temperature at vanishing density, and even at finite density, we can go with the density at higher values, even similar to the ones typical for the CPM experiment. And you can see even the rapid crossover becomes more prompt if you go to higher density. This gives us an idea that at high density, at large density, similar to the CPM, maybe we are not allowed to speak of rapid crossover. Maybe we have some prompt phase transition. To do this, or to draw any conclusion about this, we should have the order parameter, and the order parameter we have already in this model, the so-called sigmas for light quarks, sigmas for strange quarks, and sigmas for other quarks, and we have control over the evolution, the temperature evolution of all these order parameters. I mentioned that the other constraints from the theoretical point of view are the statistics. Usually we use the Maxwell-Boltzmann statistics. I'm just showing you the exponential function here, and in some studies people use the Thales statistics, which is a kind of non-extensive statistic. But be careful, this is a very special case of non-extensivity. The best way to include the non-extensivity, you have to go to the so-called generic non-extensive, in which you have another 2 parameters, not just parameter to be fitted, but it is we call them C and D parameter, in which we have the degrees of non-extensivity is included in this equivalent classes we call them. For example, if you put C and D equals to 1, you send your generic non-extensive to the Maxwell-Boltzmann, the usual one, the non-extensive one, the equilibrium one. And if we send C and D to 0 and Q, you go to the Thales one. To have the space of non-extensivity, which is not just limited to one point as a Boltzmann, which is characteristic, as I said, by C and D equals 1, 1 and 1, just 1 point, or to the Thales one, which is characterized by one line located at D equals to 0 and C goes to up 1 point something. We have a large space here. Within this large space, we have different non-extensivity. For example, we have a stretched exponential function. We have Lambert's exponential function. This gives you an idea, or enables you, if you apply them to detect the signals from the dynamics on your system. But if you insist to use the Boltzmann, you just ignore, you just oversee the entire dynamics on your system. Just to show you the powerful, or the importance of the generic non-extensive, I have compared this with the lattice QCD. As I said, lattice QCD assumes an overall equilibrium. It means we have just Boltzmann. We have just the traditional equation of the state, exponential one. The comparison with the lattice QCD, I'm just using the hadron laser gas, the thermal model, using all kinds of resonances, even the very heavy ones, and taking into account the feedback and so on, all constraints, even the ions, the light ions are also included. What I have obtained for CUD is just 1 and 1. This gives it this this gives an idea that the generic non-extensive works well if you apply them to extensive system, and as well if you apply them to some dynamic, as a case here when I have studied the particle ratios which are detected in various experiments. Yeah, these are including the dynamics in our system, and when I have compared with them and I looked for the C and D, the non-extensive, the degree of non-extensivity, I got something not like 1 to 1 and 1 as the Boltzmann, but also not 0 and 1 as Salis. We have something in between. I have obtained extended or expanded exponential function. It means the dynamics in the system becomes more. Yeah. To have an idea here about what I mean with the generic non-extensive, just here I start here with the equation with the entropy and the exponential function, and at the end maybe you can just take this partition function, the lower line here, and you apply this in your. What we have right now, what I'm trying to introduce, I have reviewed the status of measuring equation of state from the theory and in the experiment. Theory, we have constraints which are mainly in statistics. We are assuming extensive Maxwell-Boltzmann, and we are assuming equilibrium in our system. The best example for this is a lattice QCD. In the experimental side, we have limitation because in the experimental side, we don't have any access to any of the thermodynamic quantities. We couldn't measure the pressure, we couldn't measure the temperature, we couldn't measure the energy density, and so on. How to proceed further if you are dealing with situation? My proposal is that is as follows here. Is represented with in this graph here. Well, I can start with the statistical mechanics, and I can start with the hydrodynamical models and so on. Statistical mechanics, not necessarily Boltzmann. On hydrodynamics, maybe I am going to use a very old one, the Landau hydrodynamic model, the very initial one, which was long time ago, and even people have developed it in very extensively. From this, I assume to be able to have an access to the state. To do this, I'm just proposing to study the so-called squared speed of sound in the system, which is nothing but the derivative of the pressure to the energy density. If you don't like this, because in this you have to assume a constant entropy over n, you can also assume deal with the squared speed of sound as a ratio of the entropy to the specific heat. And you, as I have shown you this result. In the extensive, just for simplicity, in the extensive statistics, we can write the partition function in this way, len or log z. In this function, we have here the summation over all degrees of freedom of all hadrons and resonances, and from which we can deduce the specific the speed of sound. We need just to compare between the temporal derivative, or sorry, the temperature derivative of the pressure and temperature derivative of the energy density. When we do this in a correct, we get this expression for the speed of light. The different lines. I'm going to interpret line for line. For instance, the last line in this equation gives a relation to the energy density fluctuation, which is nothing but the average energy density multiplied by temperature, and from which I have to subtract the susceptibility. Some of these quantities we can measure, for example, the susceptibility. As the first line in this equation, I could interpret as the susceptibility multiplied by the number density, which is nothing but some multiplicities. For example, the average n squared and average average n squared multiplied by average n plus this is just velocity. To summarize what I have obtained here, the first line is average energy density, the second line is the susceptibility multiplied by some multiplicities, and the third line gives some energy density related to temperature and so on. And this is a kind of preliminary proposal on how we can measure the the speed of sound in our system, which is related to the equation of state in the to do this, or to compare with the lattice QCD, I'm comparing here resonance gas thermal model with the lattice QCD, and you can see if I go to higher densities as the bottom panels here, I also could manage to reproduce the latest data, and I have, I mean the proposed equation of state here measured or calculated in the thermal model matches well with the lattice. And if just to show you the summary of this study, which I have conducted a couple of years ago, as the equation of the state with the density, there's a kind of decreasing, very slight decreasing when you go to higher densities, and this may be limited to some temperature because we couldn't, or I couldn't at that time run this for all temperatures. Yeah, but we can do this. For example, we can limit the calculation to the temperature typical to the CPM, and accordingly we can I can give predictions for the equation of state at for the people also have done other. I'm just almost finished here. People also have proposed the hydrodynamics and started with the Landau hydrodynamics, in which we can relate the number density or the number the particle distribution, the rapidity to the rapidity itself. This I have done myself this year, and another studies related to the number of charged particles in pseudo rapidity, which could be related to this. To show some results from the second study here, there is a comparison between the NCH, the distribution number of charged particle as a function of pseudo rapidity at different energies, and you can see there is a broadening in the distribution function, and this broadening gives an idea about how the equation of state is affected by the density, and this marked equation of state just is just the expression to fit these expressions here. What we get from this fitting function is the speed of sound in this system. Showing you the result of this paper here, you can see it starts from 0.25 and declines or decreases to 0.1113 at high density, at low. The same also I have obtained. Just to summarize the talk, I mean the equation of state, which is just here limited this to the squared speed of sound, could be related to rapidity or pseudo rapidity distribution. Equation of state could also be related to multiplicities and susceptibilities. Both methodologies surely need further development to formulate complete and functioning measurement proposal in near future. But I would like to stress that to liberate and elaborate the underlying dynamic, please never stuck to the extensive Boltzmann statistics. Thank you. Thank you. Thank you.